In a previous video on this channel, I show how simple it is to use Terraform to manage a server on Hetzner Cloud and deploy a Ruby on Rails application using Kamal. In that video, I used a single server to host the application. That works for smaller sites that don't have a ton of traffic. But what if you have a web application that you want to scale across multiple servers? For that, you'll need a load balancer. Spinning up a single server on the cloud to deploy your web applications is straightforward. Once your application is set up, you can point your browser to the server's IP address or set up a DNS record to begin using your site. But if you have multiple servers hosting your application, a load balancer will distribute traffic across them through a single entry point. For web applications needing additional resources, load balancers will improve the performance and reliability of your applications by spreading traffic across all your web servers, while ensuring it doesn't send traffic to any inaccessible servers. You can set up your own load balancer if you know what you're doing, but most cloud service providers offer managed load balancers that simplify the process by handling all the complexity for you. In most cases, a managed solution will save you tons of time and money compared to doing things yourself. Hetzner Cloud offers dedicated load balancers that allow you to route traffic to your resources within their infrastructure and handle TLS termination for visitors by decrypting secure HTTPS traffic and passing the requests along to your servers. In this video, I'll show you how to use Terraform to set up and manage a load balancer on Hetzner Cloud. I'll also go through the process of creating an SSL certificate for your domain name and assigning it to your load balancer to handle HTTPS traffic. You can easily do these tasks through the Hetzner Cloud console, but getting a load balancer up and running using infrastructure as code will help you keep your systems organized. Let's get to it. For this video, I'll continue using the Airport Gap application I deployed in my previous video about Terraform and Kamal. In that video, I deployed the app and all of its components to a single server on Hetzner Cloud. For a low traffic app, having everything on one server works well enough as long as you have a good backup system and use tools like Terraform and Kamal to help you set up your application from scratch. For this demo, I've redeployed the application using Kamal, but changed the infrastructure to make the application more resilient to failure. The application is now spread across 6 servers on Hetzner Cloud. 3 servers contain the Rails application, 1 server will run Sidekick for asynchronous jobs, 1 server is dedicated to the database, and the last server is running Redis for Sidekick and caching. I created the infrastructure already and have deployed the application successfully so I can access it on every single server individually. So if I copy this IP address and I go to it here, I could see it here. I could visit the other web server, also visit it there. Everything works well. Now I want to set up a domain name to access the application and spread the load across all 3 servers that I set up and automatically handling failures by sending traffic to active servers in case any of them go down. The hCloud Terraform provider supports Hetzner Cloud load balancers, so let's get that working with Terraform. I already have the Terraform configuration to provision the infrastructure on Hetzner Cloud. I'll add a link to this configuration and the final configuration in the video description. Let's expand this configuration to set up the load balancer. The first resource I'll need to create is the load balancer itself. The hCloud load balancer resource will spin up a load balancer and we'll need to specify the name, the load balancer type, and the network zone. At the end of our existing Terraform configuration, we'll create a new resource block using the resource type of hCloud load balancer, and we'll give it a name of load balancer, which isn't a descriptive name, but since we're only creating one for this demo, it's perfectly fine. The first required argument for this resource type is the name of the load balancer. So let's call it Airport Gap Load Balancer. The following argument we need to set up is the load balancer type. Load balancers on Hetzner Cloud currently have 3 different types, the primary differences being how many targets or servers you can use and how many SSL certificates you can assign to them. For this example, I'll only use a single service and 3 targets, so the LB11 load balancer type is more than enough for me. Let's specify that in Terraform with the LB11 type, using lowercase letters. Finally, the last required argument we need is the location. For a load balancer to work on Hetzner Cloud, you must set it up in the exact network location as the target servers. Otherwise, it won't work. I spun up the Airport Gap servers on the Hillsboro, Oregon network, which is defined by the HIL or HIL location. So I'll set up the load balancer using that same location. This takes care of the load balancer provisioning. This resource won't do anything on its own because we still need to set up at least one target and one service so it knows how to direct traffic to our web app. We could also handle these using Terraform. First, we'll set up our target for the load balancer. That can be done using the hcloud load balancer target resource type. With this resource, we'll tell the load balancer which servers it should use to route its traffic when we have it set up. So we'll create a new resource block, the hcloud load balancer target resource type, and we'll call it load balancer web. The first argument to set up is the load balancer ID, which we can reference since we're going to manage the load balancer with Terraform. We can get the reference of the ID using hcloud load balancer, which is a resource type, dot load balancer, which is our identifier, and the ID, which is the attribute for it. The next argument we have is the type for the load balancer target. Here, we'll tell the load balancer the kind of services we want to identify for its routing. It supports a couple of ways to set this up, like specifying the server by its ID using the server value, or using an IP address that points to a Hetzner Cloud server located in the same network zone by using the IP value for its type. These options work, but they have its limitations. For instance, if we want to set up the load balancer to look up the target by IP, we'll likely need to use static IP addresses in case we recreate the server, and that incurs some additional costs. But the main limitation with setting the targets by server ID or IP address is that if we scale our infrastructure up and add new servers, we'll need to manually add these targets to the load balancer configuration, which is really easy to forget. A more convenient and maintainable approach is to configure the targets by using the label selector type. This setting tells the load balancer to look for any server that has specific labels set up and automatically set them as targets. When you create new servers on Hetzner Cloud or almost any cloud service provider for that matter, you can optionally set labels to identify them for different purposes. If I scroll up in this section of the Terraform configuration where I set up the web servers, we can see that I included a label, and it is setting up a server label with the value of Airport Gap Web. I can use this label to configure the load balancer to find all services with the server label set to Airport Gap Web, and it will set up all 3 web servers as targets. If I add additional web servers in the future using the same server label, the load balancer will automatically set them up as a target so I don't have to do it manually. Let's configure this in our Terraform configuration by setting the label selector argument, and the value for this argument is a query to filter the services you want to include as a target. The Hetzner Cloud API reference documentation shows different ways on how to set this value. I'll keep it simple by matching the label name to the value. So in this case, the value of the label selector would be a string server, and the value will equal Airport Gap Web, which matches the label that we already have set up. This takes care of configuring the targets for the load balancer. So far, we created a load balancer on our Hetzner Cloud account, and we set up the targets that we want the load balancer to route traffic to. We still have one more thing to configure before the load balancer is fully functional, and that's a service. For load balancers, a service is where we specify the protocol and port the load balancer will use for handling traffic. It's also responsible for performing health checks on our targets to check if any of them are unavailable, so the load balancer doesn't send traffic to a server that's not working. Let's configure the service for our load balancer. The hcloud load balancer service resource type handles this on Terraform. We'll create this block under the rest of the configuration by opening a new resource block using the resource type hcloud load balancer service, and we'll give it a name of load balancer service since we'll only have one. This resource type has 2 required arguments plus additional ones depending on the service configuration. The first argument we need is the load balancer ID. This is the same as we did before, so we could simply use the same reference for the load balancer as we did with our targets. The other required argument for this is the protocol. Hetzner Cloud load balancers can set up services using HTTP, HTTPS, or TCP. For web servers, we'll use either HTTP or HTTPS. Our web servers are currently not set up to run HTTPS traffic, so in this initial configuration, I'll set up the protocol to use HTTP using lowercase. When configuring a load balancer service using the HTTP or HTTPS protocol, we'll need to include an additional block to configure the health checks that the server will do to keep track of active servers. To do this, we'll set up the health check block. Inside the block, we have a few required parameters. The first one is the protocol parameter. Now, this protocol differs from the one we just set up for the service. The argument for the resource tells the service which protocol to use for the type of traffic the load balancer will accept, while the argument inside of the health check block tells the service which protocol to use for checking that a server is up. Typically, both arguments will use the same protocol, but there might be scenarios where you'll prefer to use a different one as a health check. Just something to keep in mind. The web servers I have set up in this configuration are running HTTP services, so that's what we'll set for the protocol here. Next, we need to specify which port the health check should ping. The application for each web server is accessible on port 80, so we'll set that as the port. The next required parameter is the interval, which is the number of seconds in between each health check done by the service. So if we set 10 here, for example, that means that the service will ping each target every 10 seconds to make sure that it's still responding. For this demonstration, I'll keep the health check interval at 10 seconds, but for your projects, do some testing to see what interval makes more sense for your needs. The last requirement to configure in the health check is the timeout. This tells the load balancer service how long it should wait for the target to respond before marking it as unhealthy and taking it out of rotation. Our web service should respond in less than a second, so I'll set the timeout to something like 5 seconds. If it takes that long for the web app to respond to a simple request, that means something isn't working quite right and it should be attended to. Again, do some testing on your projects to find the right timeout for your apps. Since the protocol for this health check is set to HTTP, we have one additional block to configure, which is called HTTP. Inside this block, we need to specify where the health check needs to make its requests. All the parameters inside the HTTP block are optional, but we should set up a few of them to specify how our application works and to avoid any unexpected health check surprises. First, we'll set up the path, which indicates the path of the HTTP request made to the target. I'm using a Rails application that has a health check endpoint already configured in the up path, so I'll use that. The other parameter I want to set up here are the status codes. This is an array of strings containing the HTTP status codes that the health check uses to determine whether a target is healthy or unhealthy. If this parameter isn't specified, it'll consider any status code on the 200 or 300 range to be successful, which is probably fine in most cases. I prefer to be more specific with these, and I know the health check endpoint in my app should always return a 200 OK status code when it's working. So I'll configure the load balancer health check to only check the 200 status code. This should be all that we need to get our load balancer fully functional and routing traffic to all our web servers. There are more parameters that we can configure for the load balancer service if we want to be more specific with some functionality, like running the health checks on a domain name or setting sticky sessions so users are always routed to the same target every time they visit the site. But this configuration should be enough for our needs. To recap what we did in this configuration, we'll create a new load balancer in the network zone where our web servers live. We'll then configure the targets for the load balancer using the labels that are set up on each web server. Finally, the load balancer will have a service that listens to HTTP traffic and makes sure our targets are healthy. We can finally add the fully configured load balancer to our Hetzner Cloud project. Going to the command line, I'll first do a quick validation using Terraform validate to make sure I don't have any issues with the Terraform configuration. So that looks good. Let's see what changes Terraform will make with these configuration updates by using the Terraform plan command. We see that Terraform will create a few new resources, starting with the load balancer and setting up the targets and the service. This all looks great, so all we need to do is to apply these infrastructure updates by using the Terraform apply command. After making sure that our plan is correct, we will apply these changes. And after a few seconds, Terraform will finish creating the load balancer and have it completely configured to route traffic to our web servers. If I go to the project on the Hetzner Cloud console and go to the load balancer section, we can see the new load balancer setup. Clicking through the details, we'll see the load balancer type and the number of targets and services that we have configured for it. It's also detected all of our services and all of the services are healthy. If we click on the Targets tab, we can see that we're selecting targets based on the server label. And if we click on this, we can see the servers it has found based on this label. Moving to the Services tab, we'll have our service configured using the HTTP protocol, receiving traffic on port 80 and routing it to port 80 on all the targets. These are the default ports for the HTTP protocol since we didn't explicitly set them in the Terraform configuration. The smaller text here shows the health check configuration for this service, like the interval, the timeout, and the path. So everything looks exactly as we configured it on Terraform, which is excellent. If we grab the IP address of the load balancer and we open it in our browser, we can now use it to reach the airport gap application. By default, load balancers on Hetzner Cloud use a round-robin algorithm, which routes the traffic to each server in order. So this first request went to the first target, and if I go again to the website, under the hood, it'll send the request to the next target. So it keeps doing that so on until it loops back to the first target again. We could also set the load balancer to use the least connections algorithm, where the load balancer tracks how much traffic it's sent to a target, and it'll send a request to the target that has the least amount of traffic. Both algorithms have their pros and cons, so make sure to choose the one that's most appropriate for your application when using a load balancer on Hetzner Cloud. So we have our application using a load balancer, but currently it's only working through HTTP traffic, which should be a no-no for any production website nowadays. Hetzner Cloud load balancers can work using the HTTPS protocol using TLS termination. Secure requests end at the load balancer, and then route the unencrypted traffic to the target through normal HTTP. This works great, but if you need to ensure encrypted communication from the load balancer to the targets, you need to set up your load balancer service to use the TCP protocol. That's a separate topic I won't cover in this video, so for this demo, I'll keep it simple by using TLS termination and let the load balancer send normal HTTP traffic to the target servers. When setting up a load balancer service that uses TLS termination, you'll first need to set up an SSL certificate for your Hetzner Cloud project. There are two ways of doing this. You can upload an existing certificate and private key if you already have one from another provider, or you can let Hetzner Cloud generate one for you using Let's Encrypt. I almost always use Let's Encrypt for SSL certificates since it's dead simple to use and it works great. So let's do that for our load balancer. However, there's one caveat that makes this process a bit more involved for us. Currently, Hetzner Cloud creates a Let's Encrypt SSL certificate for you only through Hetzner's DNS service. This is because creating the SSL certificate goes through the Let's Encrypt DNS challenge to prove that you control the domain name you want to set for the certificate. The DNS challenge process starts when an Acme client makes a request to Let's Encrypt to generate a new SSL certificate. Let's Encrypt will make a DNS query to the underscore Acme challenge subdomain of your desired domain, and if it's valid, it'll return a unique token to the client. The client then needs to create a TXT record on the DNS for the domain name using the token as its value. When Let's Encrypt sees that this DNS record is created, it proves the ownership of the domain, so it proceeds to generate the certificate. Since this process needs to dynamically create the DNS record, Hetzner needs to have control of the DNS for this to work. Hetzner can only set up the required DNS records needed to complete the challenge through its own service. Using Hetzner's DNS service is perfectly fine if you have a new domain and don't have a strong preference for which DNS service you use. But you might already have a desired domain configured on a DNS service like DNSimple or Cloudflare, which is the one I use for most of my projects. I don't want to migrate the airportgap.com domain to Hetzner just to set up SSL for my load balancer. Fortunately, there's a way to delegate the DNS challenge and the subdomain over to Hetzner's DNS to have it create a certificate while keeping your domains in your preferred DNS service. So I'll show you how you can do that. I'll go through the process of configuring the DNS zone on my Hetzner account to set it up for the Let's Encrypt validation, along with configuring my DNS provider, which is Cloudflare, to allow this process to happen. While I can also manage these steps using Terraform, it does make everything a lot more complicated since it requires additional providers and extra setup. So I'll just go through the DNS configuration manually for this example. The first step in this process is to create a DNS zone on Hetzner by going to dns.hetzner.com. Here, I'll create a new zone by clicking on the Add New Zone button. The DNS zone name is the name of the root domain that I want to use for the certificate. In this case, it's airportgap.com. In the options below, we'll leave the Add Records option configured so Hetzner can set up the necessary name server records. However, we should turn off the auto scanning for records option since we don't want Hetzner to scan and automatically set up our existing records, since we're not planning to migrate the DNS settings from Cloudflare. After we click Continue, we'll see the new DNS zone with a few DNS records automatically generated for us. The only records we really care about are the NS records, so let's go ahead and delete the rest of the records. One more thing I want to do here is create a DNS entry for the domain we want to use to point the load balancer to. So for this example, I want to use balancer.airportgap.com as the domain name to point to the load balancer for our application. So in this case, I'll create a record with the name of balancer as the domain name and set the IP address pointing to the load balancer. I'll leave the time to live value as the default. After I'm done, I'll click Continue, and Hetzner will create the DNS zone. These instructions mention deleting Cloudflare's name servers and using Hetzner's instead, which is what we would do if we plan to transfer complete DNS management of the domain. However, we're only using Hetzner right now to handle the Let's Encrypt DNS challenge, so we can completely skip this. So this finishes the configuration for Hetzner DNS to allow for the DNS challenge to generate our SSL certificate. The next step is to forward any DNS queries required for the Let's Encrypt DNS challenge over to Hetzner. Cloudflare has support for passing along DNS queries to external name servers, so we'll set that up now on my Cloudflare account. As mentioned earlier, Let's Encrypt makes its initial request to the _Acme challenge subdomain for kicking off the DNS challenge. We'll want to pass this over to Hetzner so it can handle the rest of the process. So in the DNS section for the airportgap.com domain on the DNS provider, in this case Cloudflare, we can add new NS records for each of Hetzner's DNS name servers that point to the Acme challenge subdomain. After we delegate the Acme challenge subdomain to Hetzner, we also want to delegate the subdomain that we want to use for our load balancer, since we'll keep the main airportgap.com domain under Cloudflare. We'll add these the same way as we did with the Acme challenge subdomain by creating new NS records that delegate the subdomain over to Hetzner. So one very important thing to remember here is that we need to create NS records for all of Hetzner's name servers, even though they look exactly the same. But you'll still need each name server to ensure the DNS query reaches Hetzner properly. Once we have all these DNS records configured, we can now use Terraform to manage the certificate and configure the load balancer service to use it. The hCloud Terraform provider has support for generating managed certificates using the hCloud Managed Certificate resource type. We'll create this new resource in our configuration. So at the end of our configuration, we'll create a new resource block using the hCloud Managed Certificate resource type, and we'll call it Managed Cert. This resource requires a name, which we'll call Airport Gap Certificate, and it also requires a list of domain names to generate for the certificate. You can specify multiple domain names here or even generate a wildcard certificate for all subdomains. For this demo, I'll generate a certificate for the balancer.airportgap.com domain that we set up, which is the only one that we'll use to point to our load balancer. That's all we need to generate a managed certificate on Hetzner Cloud. Let's go back to the terminal and run Terraform plan again to make sure that we set up things right. And it looks like it's going to do what we want, which is to create a managed certificate using the balancer.airportgap.com domain. So let's go ahead and apply this using Terraform apply. This kicks off the Let's Encrypt certificate generation. If everything is set up correctly, we'll have a new SSL certificate created in about a minute. If you receive an error during this process or Terraform attempts to apply this resource for more than a few minutes, the likely culprit is your DNS configuration. So double check the DNS entries on both Hetzner and your primary DNS service and give it some time to make sure that all the DNS records are propagated. So in less than a minute, it looks like our managed certificate was properly created. Going back to our project in the Hetzner Cloud console, we can go to the security page, and under certificates, we'll see the new managed service ready to use. Now that we have this certificate, we need to update the load balancer service to use TLS termination so we can send encrypted HTTP traffic to it. Updating the existing load balancer service to support HTTPS is pretty straightforward in Terraform. First, we need to switch the protocol argument from HTTP to HTTPS. This sets up the service to use TLS termination. One thing to note is that we cannot switch the protocol of an existing load balancer service on Hetzner Cloud. If we were managing this infrastructure manually through the Hetzner Cloud console, we would have to delete the existing service first and create a new one after. However, Terraform will automatically handle this for us simply by updating the argument, which is a nice benefit that infrastructure as code tools have. Since we switched the protocol, we'll need to add some additional configuration to the load balancer service. We'll have to set a new HTTP block to change some of the defaults for HTTP configuration. Inside the block, we'll set the redirect HTTP parameter and set it to true so that any unencrypted HTTP connections to the load balancer are redirected to HTTPS. This is an optional step, but in most cases, you want all of your website traffic to go through HTTPS. One additional parameter that we want to include here is the certificates parameter. This parameter accepts a list of the SSL certificates that the load balancer will use to enable the encrypted connection between the client and the server. This parameter accepts a list of certificate IDs that we have for our Hetzner Cloud projects. We're managing this certificate in Terraform as we just created it now, so all we need to do is add the reference to its ID here using hcloud manage certificate dot manage cert, which is its identifier, and the ID, which is the attribute. These updates are all we need to reconfigure our service to use TLS termination. As we always do, let's run Terraform plan to ensure these updates are doing what we expect. As we can see here, Terraform noticed that we're changing the load balancer service to use TLS termination, so it'll force a replacement of the service by deleting the old one and creating a new service. This looks good, so we'll apply the changes with Terraform apply. In a few seconds, the old service was deleted and the new one was created to use TLS termination. Checking the load balancer in the Hetzner Cloud console, we'll see the updates have taken place. In our service, we'll see that we'll be able to use HTTPS to connect to the load balancer using the domain name we set up. So let's see if that's working. If I open a new page on my browser and I go to https balancer.airportgap.com, we can see that our load balancer is working using HTTPS. The domain name setup works as expected, and we're using encrypted traffic between the client and the server. With this, we now have a fully functional load balancer for our web application on Hetzner Cloud using TLS termination. This video showed how we can use tools like Terraform to set up and easily manage a load balancer on Hetzner Cloud. We also set up a domain name from an external DNS service to create an SSL certificate for encrypted communication between a user and the load balancer. Using infrastructure as code to handle these tasks instead of clicking buttons on a website helps build consistent and repeatable systems, making it much easier to manage as your organization scales. As a reminder, the way we set up the load balancer in this video handles the encrypted connection up to the load balancer, where it decrypts the request and passes it along to one of the target servers. If you have strict security requirements, you'll need to set up a way to encrypt the connection between the load balancer and the targets. I didn't cover that in this video, but let me know if you'd like me to cover it in a future video. If you found this video helpful, consider subscribing to this channel for more tips on helping developers ship their code confidently, from development to deployment. You can also check my website for more in-depth articles covering Rails, testing, DevOps, and other software engineering topics. Thanks for watching, and I'll see you in the next video.